So enough of me. Over to our speaker.
So Aaron, if we can invite you up to the stage by clicking on the presentation button at the bottom.
Oh, yes. I'm going to try. So on this platform, there isn't a native recording facility, but I'm going to try and record this session through OBS. So fingers crossed it works out.
Can you hear me?
Yeah, we can hear you. But I'm going to drop off the stage. I think Michael is too. But we'll come back on and give you any help if you need anything. So thank you, Aaron. And Michael and I are really looking forward to having you on as a guest tonight. So this is going to be an awesome talk. And thank you for joining us. And we'll hand it over to you now, Aaron.
Thanks, Aaron.
Thank you, Glenn and Michael. Thank you both for having me. It's really truly an honor. By the way, this is a sweet platform. This is probably one of the best run COVID, probably even outside of COVID events I've been to. So pretty excited. I'm also excited to be on stage with Glenn. You see, I have his book here. So I recommend you pick up a copy of that as well. All right, so without further ado, I'm going to get started in the presentation. Yes, that is me with the green hair, and so this presentation is going to be on security chaos engineering. At the bottom there, you'll see my Twitter at Aaron Reinhart. My DMs are open. If you are interested in learning more, or you need additional resources, I do respond to DMs on Twitter, LinkedIn, or emails. So I do mean it, but most people don't even reach out when I really do mean that. So, all right, without further ado, I'll get started. So I'm going to talk a little bit about chaos engineering today. I'm going to talk about security chaos engineering, talk about what it is, what it isn't. I'm going to talk about some use cases you can apply for from a DevOps, DevSecOps perspective. I'm going to talk about that ChaoSlingr, an open source tool that I wrote about 4.5 years ago. And how it can be used as an experiment framework. I'm also going to go through an example security chaos engineering experiment, and then we'll open it up for questions. A little bit about me. I am the CTO and co-founder of Verica. Verica, we are the creators of chaos engineering. Casey Rosenthal was my co-founder. He's the CEO of the company. He created chaos engineering at Netflix. He wrote this O'Reilly book on the topic. And also, I wrote the O'Reilly book on security chaos engineering, well, the first one at least. We actually have one of the contributing authors here tonight, Kennedy Takura, who's also available in the audience to answer questions later. My background is I'm the former chief security architect at UnitedHealth Group. For those, for most Europeans and folks in the UK, probably not familiar with other healthcare companies, but UnitedHealth Group is the largest private healthcare company in the world. So there's about 400 companies. I also have a background working for the Department of Defense in the United States. I actually worked at NASA Safety and Reliability Engineering, and I'm a frequent speaker and author on the topic. So getting started here, is that you don't seem to be, with all we're doing in cybersecurity, we don't seem to be getting any better at the problem. Breaches and outages and incidents, or breaches, outages, or incidents seem to be happening more often and seem to be getting bigger. And why is this? What are we doing wrong? Well, the problem is rooted in complexity. Is that our systems have evolved beyond our human ability to mentally model their behavior in our heads. They're just too big. The size, scale, speed, and complexity of modern software is daunting. So if you see this image on the bottom left-hand screen here, left-hand of the screen, you'll see every dot, and they seem to be connected in a web. Actually, each dot represents a microservice. Okay, it's rumored that Salesforce's CRM is over 100,000 microservices. It's very simple. These, I thought microservices were supposed to be better than the monolith, but it seems to have made a scale and speed and as a result complexity a new era of challenge for for modern software. And it used to just be Facebook, Apple, Alphabet, Netflix, and Google that were building these large-scale microservice architectures. But now it's everybody. People are moving off the monolith, adopting CI/CD, adopting microservice architectures, going to the cloud, and we're now starting to see problems that we never thought would ever happen. So where does all this complexity come from? Well, I just mentioned a few of these from things like Kubernetes, containers, distributed system architectures, microservices, CI/CD, auto canaries, circuit breakers. These technologies are actually helping us deliver value to market faster than we've ever delivered before, but also increasing the amount of complexity that we're seeing inside of the system. And it makes it very difficult for any one human to understand what is actually going on in the system. So a newsflash, on the right-hand side here, you'll see the new OSI model. It's now software. Software is officially taking over. The one thing about software is that software never decreases in complexity. It only increases in complexity because software, even if you wanted to make the system more simple, you would have to change the system to do that. And then there's an inherent relationship between change and complexity. Furthermore, there's an old saying in software that there's no problem in software that can't be solved through another layer of abstraction. Well, at speed and scale, we're starting to see those layers of abstraction cause problems. It's not about trying to simplify the system, because you can't actually simplify it, because when you simplify it, remember, you're changing it. In order to do that, you're increasing the complexity. It never decreases. Software doesn't. Part of where complexity comes from is things like Conway's Law. Is that Conway's Law states that organizations are destined to design computer systems that reflect the way they communicate as a business. So that complexity of the way the business operates finds its way into the business. So it's really not about simplifying the system. It's about learning to navigate the complexity through continuous adaptation and learning. That's what chaos engineering is really about. So to further illustrate this, I early on in my journey in chaos engineering, it's hard to kind of explain what we're doing sometimes in chaos engineering. I was at one of the world's largest payment processors, and I was overhearing a conversation between Casey and the principal engineer. They were talking about how their flagship application, it was the #1 application for the company. It was the legacy system that made all the money, processed all the payments for the provider. And what they wanted to do is they wanted to modernize the system and move it over to Kubernetes. But they were concerned because this legacy system is stable. Its engineers feel confident in how it works. The documentation is somewhat accurate. It rarely has an outage or an incident. It seems stable. But I started thinking to myself, was that system always so stable, right? Or did it become stable through a series of surprises or unforeseen events, meaning outages or incidents? Often those outages or incidents are what inform us that our understanding of the system wasn't exactly what we thought it was. And then so we learned that the system worked a different way. We remediate and we make changes, and over time we have developed this better understanding. The system becomes more stable. But the problem with that is that this process of learning as a byproduct of system outages and incidents is costly to the customer, or costly the impact of productivity for engineers. And what we're doing with chaos engineering is we're sort of accelerating the process without impacting customers. And we're doing that by proactively introducing these failure conditions into the system to try to surface inherent failure in the system before it manifests in the customer pain. And that's the value. This is a proactive exercise. When nobody's freaking out, nobody's worried about losing their job or being blamed for an incident, we can proactively discover these problems, fix them so they don't manifest in the customer pain. And that's the value of this stuff, because when you're in an active war room for an outage or an incident, people freak out, and it's not a good learning environment. So another thing we like to forget, and this is easy, I do this myself, is we forget that system engineering is a messy exercise. It's very messy. To illustrate, in the beginning of a systems evolution, we love to think that a system looks like it does here on the right, that there's a nice 3D diagram, there's a, there's the code, there's the images, there's the staging, and this production environment. We have it all figured out, right? We've got the system, we understand how it looks. In reality, it almost never looks like this. Because what happens is after a few weeks, a few months, there's an outage on the payments API. We have to hard code a token. Marketing comes down and says they got the pricing model wrong and they have to refactor the pricing service. We slowly, or this expired certificate, Google hires one of your best engineers. Constantly, our system slowly drifts into the state of unknown behavior because it's constantly being changed. We're constantly in there changing the environment. And it drifts beyond any one person's understanding of what's going on, especially when you have microservice type of architectures and team models, where you've got 10 microservices, you've got 10 different teams delivering on 10 different services, maybe delivering on the same schedule, maybe slightly different schedules, maybe 10 times a day, 10 times a week. But there's not actually 10 microservices. There's probably 5 to 10 of each. So immediately out of the gate, you have at least 50 to 100. But that's without including the fact you might have older versions running, because microservices are not dependent. They're not independent. They're dependent in how they operate. They require functionality from other services. You see how the complexity in the web of scale starts to find its way in here. So, and after years, we just slowly drift into the state of where our system doesn't reflect what's in our head, and what our head is not what it is in actual reality. So in the end, as a result, our systems have become more complex and messy than we initially remember them being. So what does all this stuff have to do with security, right? Well, I'm getting around to it. So I want to illustrate something here, is that one of the things I've discovered and why this practice is so valuable is that, so as an engineer, my job, so I need the flexibility and convenience to change something, change an object. And what I'm doing is I'm attempting to deliver business value to a customer, because that's my job. I'm constantly changing because I'm delivering customer value. While security, when designing security is a context dependent discipline. Is that you must understand the object, you must understand the object and the context around the object to know what needs to be secured about the object, whatever it is, user, security group, whatever it is. Whatever, you have to understand the nature of what it is to understand what needs to be secured about it. Well, that forces security to be in somewhat of a stateful design. And what's happening is that we are designing good security controls, good capabilities. What's happening is that we're constantly also changing the objects in the environment to deliver towards customer value. What's happening is that we're starting to see this divergent behavior. The control is not necessarily changing along with the trajectory towards customer value. And what's happening is we don't know this is happening until there's a problem. So with chaos engineering for security, what we're doing is we're introducing the condition by which we expect to be true about the security for that object. And it'll make more sense when we do an example here in a little bit. So chaos engineering, we like to describe it, we like to loosely define it as an area of experimentation, not sort of traditional testing. But by the way, I want to make it clear though, instrumentation in general is tremendously valuable. I'm not saying that testing is not a valuable thing. This is a new sort of instrumentation for a post-deployment world. And that's really what we're targeting. It's not CI, not CD, but the post-deployed running system is what we're actually instrumenting. But testing, we like to describe as the verification or validation of something we know to be true or false. It's sort of a binary thing. We know what we're looking for before we go looking for it. Or you can think of it as a known, right? And whereas with experimentation, chaos engineering, we're trying to derive new insights, new context, new information that we previously did not know about the system. Which we do that through asking the system a question we believe to be true. I believe under X conditions, that the system responds with Y. That's what I'm designed to do. We introduce that condition to the system and observe whether or not that's true or not. I will tell you, I've never actually seen a chaos experiment succeed the first time it was ran. So how do we typically discover when our security fails? Well, we typically discover when there's an incident. Usually we discover through some sort of footsteps in the sand or some sort of vanishing trace, meaning security observable events, alerts, log events, but there's also the problem is that software security observability is one of the biggest unsolved problems in security. Furthermore, if you're discovering there's a problem with the effectiveness of your security through a launching of a security incident, it's probably too late. It means that B I described a little bit ago, you diverged a long time ago, and now you're finding out when it's actually a problem, and that's not a good time to discover that there's an issue. So what typically happens during a security incident? Well, we've all probably been involved in some in a security incident or outage in some fashion here, but people freak out, people are worried about being named, blamed, and shamed. Like, oh, I know I shouldn't have pushed that code. I know I shouldn't have made that change at 3 a.m. People are concerned, and they're worried. This is not a good learning environment, right? Because it's not about what happened typically. It's about get that thing back up and running. We're losing money. And that's what it quickly becomes after 15, 20 minutes of there being an outage or an incident. So we don't do chaos engineering here. We do chaos engineering here. We do it when nobody's freaking out. We do it when there isn't an active war room or an incident. We do it when eyes are wide open. We're not constrained by blinders. And so we're proactively introducing conditions we expect to be true to ensure that our understanding of the system is what it actually is. And because there's no active war room, we can observe things we never could look at before. Maybe we could take a better look at the logging events. One of the great things about that security chaos engineering provides observability is that you can proactively introduce incidents into the system and ascertain, proactively, did we have the right log information? Had this been a real incident, did we have the right context in order to know what runbook to kick off, who to call, or what control failed, or what system this came from? But when there's an active incident war room, you're stitching things together, trying to figure out what happened because there's a problem. You're not able to proactively look and judge and measure the value of the feedback from the system. And just a point on that is that if a log event or alert doesn't make sense to a human, you should get rid of it. That's the whole point of observability. It's that you should be able to understand what's going on inside the system through a system's external outputs. So chaos engineering, I've kind of described what this is a little bit, but Netflix originally defined it as the discipline of experimentation on distributed systems in order to build confidence in the system's ability to withstand turbulent conditions. So another way of saying this, it's the discipline of proactively introducing turbulent conditions into a system to try to determine the conditions by which a system or service will fail before it actually fails. Excuse me. So chaos engineering, another myth is that our system is already chaotic enough. You're just going to cause more chaos. No, not really. What we're trying to do is create order from the chaos that's already within the system. And a lot of that chaos comes from the fact that we've now manifested complex adaptive systems in the form of large-scale computing environments, and they exhibit certain behaviors that are, this is where chaos theory comes from. It comes from the whole butterfly flaps its wings. Well, that's nonlinearity, and we're starting to see that in our large-scale computing environments. And so what we're trying to do is establish order in that world. So there are several books on the topic. There's the main O'Reilly book. I will have links to download the digital copies of all of these for free at the end of my presentation. But we'll also give you away some physical copies in the giveaway as well. So what is security chaos engineering? Well, really, in essence, it's really the same thing as applied to the components and context and use cases in cybersecurity. So another thing we like to say in the domain of chaos engineering is that hope is not an effective strategy. It worked in Star Wars, but it doesn't work in engineering. I've always liked to say as an engineer, engineers don't believe in two things. We don't believe in hope. We don't believe in luck. Either works or it doesn't. If we do believe in something, it's instrumentation and data and feedback. But we can't just rely on the hoping our system works the way we think it does. So it's really what we're trying to do is proactively understand where our gaps are in the security and expose them and capture them before an adversary can take advantage of very simple types of things. And when I give examples of these, security chaos experiments are very simple in nature. They're not sophisticated attacks. It's not any. We're not doing a complicated type of attack scenario. It'll make sense here when I show the example, but it's usually typically very simple failure modes, and you'd be surprised how much we don't catch. So one of the main use cases that I applied security chaos engineering to at UnitedHealth Group was incident response. Because the nature of incident response is that it's a response, and that you don't know, it's very difficult to measure proactively, when any objective information, like how quickly we're responding to certain types of incidents. Well, the entire process of security incident response is somewhat subjective in nature. Is that I'm missing a slide here. But anyway, is that no matter how many people you have, how many controls you have implemented, no matter how much money you have spent on your security, you still don't know a lot of things. You still don't know where they're going to get in, why they're getting in, how they're going to get in, and who's trying to get in. You don't know these things. You're kind of hoping everything you put in place is ready to respond to the scenarios you designed them for. But the system will almost never works the way you think it does. And what we're able to do is we're able to proactively introduce these conditions we expect to occur within the system and verify that, yes, under these conditions, we got great log information and we correlated alerts and the controls worked and fired as they're supposed to, or we had the right people on call, or the run books were actually correct. Or you get the idea. We have to proactively do things we've never done before. Furthermore, it's very difficult to measure metrics in an incident because you're responding to when the event occurred. Like, you don't really know when it began per se. You might have had the right information, but you might have been responding to a cascading issue. But with chaos engineering, we're actually causing the event. So now we know the point of entry, and we can start seeing how long it really took. And so we can look at it with a new objective lens that we couldn't look at before. So use cases, like I said, incident response, security control validation, security observability. And also it's important to recognize that, by the way, everything I'm saying here is documented in this book. We're also writing the full O'Reilly book on security chaos engineering. That'll be out towards the beginning of next year, 2022. But coming back to it, compliance. So every chaos experiment, whether it's availability, stability based, or it's security engineering based, has compliance value. Essentially, you're proving whether the technology worked the way you thought it did or had it documented. Really, all you have to do is map your chaos experiments to the right control mapping for your compliance framework. Think AU01 or your monitoring 02, whatever it is, whether it's NIST, PCI, you get the idea. So this is what I was talking about earlier. This is the slide I was missing, but really this is more about the incident response. It really helps us be proactive in our preparation instead of relying on hoping that what we prepared for works. We can actually instrument and verify that we are ready, we are effective. My boss, when we first released ChaoSlingr at UnitedHealth Group, one thing he said to me that was really impactful was, he said, "Aaron, I love how this validates our technology capabilities, but it really helps me know that my incident response process is sharp." And that was the first time I realized that, hey, there's value in the incident response measurement and effectiveness. So is that ChaoSlingr. This is the tool that we wrote at UnitedHealth Group. Since I have left, the tool is somewhat deprecated. We also, Kennedy Takura is in the audience. He wrote a tool called Contacker. It's also called, he changed the name, it's called CloudStrike, which I was confused. But anyway, ChaoSlingr still represents a framework on how to write security chaos engineering experiments. There's really 3 different functions you need. There's Slinger, there's Tracker, and there's Generator. And it's somewhat self-explanatory on the open source repo in GitHub. And there are additional tools coming. There's a few folks in the EU writing a Kubernetes tool. But really, here's the thing. You don't need a tool to do this stuff. You can do it in Bash. You can do it manually if you need to. I highly recommend you do it in an automated way, like a scripting way, like Python, Bash. But you don't need a fancy tool to do this. You can do this in writing your own automation. So the primary example that when we released ChaoSlingr, we needed to release an experiment that everyone could understand what we were doing. So the main experiment, this is when my eyes started opening and my eyes opened wide to the value we were creating. But we were very new to AWS as a company. Remember, the world's largest healthcare company, and we were going to the cloud. And so one of our assumptions is that for some odd reason we still see misconfigured network ports and our unauthorized port changes still today are still a problem, even though we've been solving for that for 30 years, right? It could be that it happened on accident, or somebody didn't understand flow, somebody entered the change wrong. It could be that somebody didn't understand how to manifest the change in a software-based cloud environment. Lots of different things can make it so this is not a malicious kind of accident. But anyway, we saw this happening quite a bit. So our assumption is that we were very firewall heavy dependent, very, very dependent on our firewalls. And our expectation was our fancy firewalls would immediately detect and block that type of behavior. It would be a non-issue. Well, so we started actually proactively injecting either opening or closing a port that wasn't already open or closed. We started doing this in our AWS EC2 security groups, and we started finding out that the firewall only actually detected and blocked it about 60% of the time. And that was actually due to a configuration drift issue between our commercial software environments and our non-commercial software environments in AWS. No problem. Remember, there was no incident or outage, no war room. We proactively found out, hey, we got a problem here, and we fixed it before it manifested into a problem. Second thing we learned was that the cloud native configuration management tool caught and blocked it every time. So something we barely paid for, barely knew how it really was working in the environment, was working better than we could have expected. So that was the second thing we learned. The third thing we learned was, UnitedHealth Group, we didn't have a sort of a SIM. We wrote our own security big data lake and security analytics sort of tool set, and I had very little faith that solution was going to generate alert from AWS. But it actually did. It actually generated alert, and the alert went to the SOC. So that's the third thing we learned, is that the alerts worked. Great. I had very little faith. Now I had confidence that it did work. But so the SOC, the Security Operations Center analysts, got the alert, but they couldn't tell which AWS it came from. And as an engineer, you could say, Aaron, you can easily map back the IP address and figure out where it came from. True. But remember, if this were an active incident or outage, that could take 15 to 20 minutes to do that. And UnitedHealth Group, during open enrollment, that's the period where companies sign up for new healthcare. 1 minute of downtime was over $1 million. But because we proactively did this, and there was no outage or incident, we were able to address the issue, add a metadata pointer to the alert, and is a non-issue, not a problem. So we were able to proactively address these things where nobody was worried about being blamed and ashamed, and fix them before they manifest into real world problems. So here's the link to the Security Chaos Engineering book to download it for free. Here's the link to both. If you would like, I could talk about additional security chaos engineering experiments in Kubernetes, for example, or AWS. I'm kind of open to talk about different experiments, but I'm going to leave this slide up here. That's okay. Oh, whoops, sorry. Let me reshare that. I messed that up. Let me fix that. Here we are. Okay, great. Great. I guess I'll open up for questions while we do that. I'm not sure if this works, by the way, either.
Well, the audience could feel free to join us on stage, or maybe post their questions in the chat and we can relay that back, or we can break off and we can huddle up in the group and interact live. So any questions?
So I've actually got a question. Sorry to start the ball rolling, but the question I've got for you, Aaron, is obviously with traditional chaos engineering, you're talking about of the security pillars of confidentiality, integrity, and availability. We really only talk about availability. I'm guessing what security chaos engineering needs to do is look at integrity and confidentiality as well. I mean, integrity is probably the biggest part of this. Would you agree with that? Or?
You know, so let me preface my answer quickly by saying, just because I was the first sort of to start doing this, doesn't mean I know all the ways we can generate value in doing it. Right? I'm learning, like Capital One took my work and did it a whole different way. You know, so the Cardinal Health, no, but like, yes, so the CIA pillars are a good way to think about experiments. But there's probably some experiments around data integrity and data privacy that I have not really, attempted. There's probably some around DRM, maybe DLP type of things. We can inject those conditions and ensure that, because DLP's never been a good security control. I don't know your perspective on it, but there's probably a lot of experiments there. It's just I myself have not, explored that. I don't know if I kind of helped answer or kind of.
No. Yeah. I mean, with chaos engineering, as I say, it is more about the availability. But what differentiates, I guess, security chaos engineering is that you are challenging or experimenting against some of the more, the integrity and the confidentiality, and you've got to think about ways that you're going to do that. So you can't, it's not as simple as like just saying, well, if we make this password in the clear, then something might happen. It's what's the offshoot of a password being exposed, or
yeah, exactly, Glenn. So exactly. So in that case, let's say we introduce let's say we have HashiCorp's Vault in play. We've got secrets management solution. What happens if we expose a secret? Like, does GitRob in our Git repo detect it? Like if we know we don't have a security capability for that, we're not going to learn anything. We already know it's broken, right? But like what we're doing is we're instrumenting our assumptions about what we put in place. So I believe whenever there's a key, a token, or a password or a secret that's exposed in my GitHub repo, that the following XYZ control is supposed to fire, send alert, detect, and we proactively introduce that condition. You can do it somewhat synthetically, so you're not actually causing an incident or outage, but you do it to just see if the control is still actually functioning and firing. And I'll tell you what, even though that sounds so simple, so low-hanging, kind of like duh, you'd be surprised how little you actually catch that. Yeah. And I can explain why that happens if you're interested.
And how many times do we hear of stories of certificates expiring and not being caught? Chaos engineering is a great example of where you can use that proactively to say, what happens if we expire a certificate? What happens? Do we see a response to that, and can we fix it before it actually becomes an incident?
That's security certificates, DNS. Interesting. We were doing some experimentation at Verica on some of the traditional DNS types of attacks we used to see in old school networking, like ARC cache poisoning, DNS cache poisoning. Those old school kind of networking flaws have found their way into the software-defined networking world, and they're not as easily caught. So from a Kubernetes perspective, there's a lot of experiment surface there. But a good example, I think Sarah is asking about a Kubernetes example experiment. So one of the things we actually run at Verica, for example, is we actually have a vulnerable image. We launch a vulnerable image in a container in a Kubernetes cluster. And we time how long it takes, whatever control, Twistlock, Aqua, Capsulate, whatever tool that's there, how long it takes to detect and block it. And, you know, my initial assumption when we came up with this is like, guys, that's too simple, right? Like that's going to be caught 80, 90% of the time, and it'd be a non-issue. Well, it's actually the exact opposite, you know, and it really kind of like opened my eyes. Is like, you know, it's because, you know, it's not because those tools are bad tools. It's that the, you know, we initially designed the tools for the app or the environment or the cluster at a certain point in time, and we validated that it was effective at that point in time. But after that point, the environment changed, or you know, or we launched new environments, so we redeployed, or we changed the context around the deployment, and you know, the security capability could no longer download its manifest, so it was failing silently, or it couldn't, or didn't have the right network permissions to actually execute, or what have you. You know, this is the messiness of what I'm talking about with modern engineering. So it's so that's an example. You know, another good example is you know, around Kubernetes. You can apply these same examples to a lot of different you apply these examples to a lot of different types of environments. Another example would be that the networking. So Kubernetes. So Amjad Hussain is asking about emission controllers being able to block vulnerable images from being deployed. Well, you know, Kubernetes is a finicky thing. Is that it's so heterogeneous in how the deployment model, in that, you know, yeah, exactly. Ryan, spot on. But like, you know, no matter what you have in place, or rule sets, policies, you have control, you have an open source capability, you have, you know, are you sure that those things over time? So when you run a chaos experiment, it's more the first time you run it is an exploratory kind of phase, right? So you're exploring, you're trying to ascertain whether or not what you put in place is actually functioning under the conditions you expect it to function. You know, if it doesn't, you'll learn why it didn't, and then it becomes more of a regression type of test, right? Where it's like you constantly run it periodically, and you know, and that way you can, you know, measure over time, like, did we drift? Did the environment drift away from effectiveness of that capability? Let's see, can be set up. Yeah, exactly. You know, another experiment you could do is connectivity between pods and pods containers. You know, to ensure that like the right things can communicate to the right things. You know, you can say at certain points in times when you're scanning, or you're, you know, or you're configuring things and you're validating it. You know, that X pod or container can only communicate to, you know, the right things that I expect it to. But you know, we're constantly making changes to the environment, and we're needing that flexibility to change network ports. You know, we're really only designing with a few things anymore, yeah, that's exactly right. You know, how is it that so many Kubernetes clusters end up exposing the Kubernetes API to the internet? I don't know. You know, it happens, but like, you know, I don't believe a lot of this is actually people maliciously doing it. It's just that everybody's kind of in the system, changing things and making changes, and we need to ensure that the security we put in place is doing what it's supposed to, or what it's designed to do.
You're on mute, mate.
Sorry, I keep doing that. Yeah, we have another question from Ryan. This is quite a good question because it probably plays into the answer about observability. But how is coverage and success measured using security chaos engineering?
Coverage and success. You know, that's a really good question. You know, that's a really good question. I don't know. You know, I'm not sure you can ever get complete coverage. You know, so if like you were trying to, you know, like get complete coverage for PCI or CIS benchmarks, you know, for our NIST, for or any of those for Kubernetes, you'd have to base it upon, but like you'd have to do these experiments. So like back to the ChaoSlingr example, just because you ran it on one environment doesn't mean you're okay in all environments, right? There's like what we exposed was initially was that big drift issue between our commercial and non-commercial software environments. But there's a big, how environments are configured are going to vary across different applications and deployments but that's a really good question. That's actually something we should probably address going forward, is figuring that out. But this is still early days in doing this, and that's definitely something I'm going to be thinking about. That's a really great question, Ryan. Thank you. I'm willing to say what I don't know.
Thanks, Ryan, for asking the question. Is there any more questions that people have?
There was another one about examples of compliance monitoring. Does that, do you see how that fits in?
Definitely. So all chaos experiments. So here's what I love about compliance with chaos engineering, is that if you do it right, compliance is a byproduct of good engineering. What do I mean by that? Is that all chaos experiments, whether they're availability, stability, performance, or they're security engineering based, have compliance value. It's really about mapping it to the right control framework. I don't think I had an example. I could maybe share an example of how it maps, Kubernetes would map to PCI, but really you map the experiment. Let's say, for example, let's say you had a pod node reachability experiment from a network, pod node network reachability experiment. And what I mean by that is pod just connecting to all kinds of things, trying to connect to it, things trying to connect to it, trying to understand what can connect, ingress, egress, trying to ascertain that the PCI zone couldn't communicate externally, that other environments are like the DMZ that you have declared in your architecture couldn't communicate to the environment. That would be, there's several PCI controls that map directly to that. It's probably a crude example, but I have a spreadsheet somewhere that shows how a lot of these map. But this is why coverage is a thing. It's okay. Andreas, I work at a large bank in the process of moving a lot of functions to the cloud. How would you try to convince the old guard about chaos engineering would be a beneficial investment? I will tell you that as a company, as the people that created this space, the number one sector that is adopting chaos engineering the fastest is banking, the financial world. And it's they're doing all levels of maturity, right? Some of them are just breaking things. The problem is, so the reason why we built Verica, we built, our tool is very deep from a product perspective, in that we don't just break things, right? We tell the story, is that we inject a failure condition that people really see in Kubernetes. You'll see a lot of the chaos engineering tools out there that just kill a VM, kill a pod. The question is that really a failure mode you're seeing? The key is to replay real world failures that you see in those technologies, because Chaos Monkey is exactly what Netflix was seeing. AMIs in AWS were disappearing. So what Chaos Monkey does is kills AMIs, I've seen a lot of banks actually adopt chaos engineering, and it's really about just checking to see if there's any context. How would you convince the old guard? There's actually a lot of great context in the chaos engineering book on how to make the argument, but it's really about being proactive and servicing failure from an outage perspective, so you're not constantly responding to fires, and you can be more proactive about understanding the brittleness and the weaknesses of the system, so they don't manifest into costly issues. But it's important that you focus. Part of the reason why I was explaining this earlier, part of the reason why we built Verica is to accelerate the time to value. Because when you start off doing this stuff, it feels a lot like breaking things. Okay, but if you're it needs to be about value that you're generating. So it could take anywhere from 2 weeks to 2 years to really start generating value. So you really need to focus on understanding the craft, doing it in more environments, maturing into doing it in production eventually. Although a lot of banks actually don't do chaos engineering in prod. A lot of them do it in non-prod. But you can learn a lot in non-prod as well. I've also, just to add to that, Andreas, a lot of the exchanges, out of the worldwide exchanges are also doing chaos engineering. So it's not just the banks, it's the things the banks rely on as well. If you'd like to reach out to me, I can connect you with folks at the big banks doing that.
Yeah, I got another question there from Carlos. So what mental models or perspective changes do you use to work backwards in understanding what could go wrong in a complex system with many interdependent components?
I knew I was going to get great questions. I always get the best questions from the DevSecOps or software security community. Yeah, so this was actually initially kind of hard to wrap my mind around this. Like, a lot of security people think attacks and they really go to that purple teaming, red teaming, pen testing, or breach and attack simulation model. That's not what we're doing. We're rejecting one single failure. Very simple. We're not doing a Node.js mass assignment attack or a clickjacking attack, or think about it, large scale microservice environments, distributed systems. If you make a bunch of changes, it will ripple throughout the system. It's very difficult to figure out what worked, what didn't, what broke, so you have to make sure you're accounting for that. But also, so how do you think about it? I like to say that what is past is prologue. And what I mean by that is that what has happened before is likely to happen again. So a good way to look for good experiments is to get together in a game day exercise and talk with different stakeholders from the product team, the incident response team, the database team, the front end team. Say, hey, I believe when this condition on the WAF occurs that it's supposed to fail over this way or do this or do that. And then if everyone's in agreement that that is a condition you believe to be true, you can exercise that as an experiment. Or you can actually go looking at prior incident data. The problem with this is that very few people document their incidents very well outside of a Sev 1. Everything is usually pretty crappy from a documentation perspective, but is that you can find out what has happened before and see whether that is still happening by replaying it in the environment. We're getting a lot of questions here. So what I'm saying is that what has happened in the past is likely to happen again. So past incident data is a good way to look for experiments. Can chaos engineering help you differentiate between a short-term mitigation that can be applied rapidly and perhaps a more strategic remediation? Let me think about that. Potentially, I mean, I need more context on that, but on what you mean there. But it's what's funny though is that a lot of strategic remediations have a lot of trouble from a governance perspective on change being applied in the environment. You get all kinds of CCBs, change control boards, or people saying no to a change that they really don't even understand the change, and the engineers that are actually working in the environment say, no, we can't do that, or no, we need it, or else we can't do what you think it needs to do. We don't often listen to people that actually are building and instrumenting the system, which is very problematic, is that they're the only people working with the system and building it are the only people that really understand how it works. So it's important to take their perspective at a priority. But my point is that we often, during an outage or incident or war room, and security people will make a change that we would never make in a real world scenario, right? Where all of a sudden, throw in a security capability, open source one, just like HashiCorp's Vault. We couldn't get HashiCorp Vault purchased because the management wouldn't allow us the money to purchase it. But during an incident, we'll throw in the open source version that doesn't have the capabilities we need to be compliant. We cause a new problem. So what that to me, that's what came to my mind between strategic and tactical kind of remediations. But yeah, I think you can instrument both strategic and tactical decisions through chaos engineering. And like I said before, it doesn't have to be on prod, but you want to get there eventually. And there's a lot of context in both books about maturity, how you get to doing it in prod. But that's where the problem's going to happen. And there are techniques from a distributed system perspective on how you can you can run chaos experiments in prod and without impacting the entire user base. Netflix uses something called CHAP, the Chaos Automation Platform. So part of that, my co-founder built that at Netflix. So part of our product at Verica utilizes this, but it has a way of actually using reverse proxies and sort of canary deployments to create multiple copies of a service. So you're only impacting a partial group of the user base instead of the whole 100% of the users.
But thank you, Aaron, for coming along tonight. Really appreciate it. Great talk. Lots of stuff to think about. And if you'd like to head over to the speaker. But in the meantime, everyone give a round of applause to, yeah, well, thank you.
Thank you.